Here we are moving into section 2.1 of our college algebra course, which is going to kind of expand a little bit on our linear topics that we've been working in chapter 2. And this one is referring to fitting linear models to data. So in the real world, rarely do things follow trends perfectly when we expect the trend to behave linearly or when inspection suggests that the trend is behaving linearly. It is often desirable to find an equation to approximate the data. Finding an equation to approximate the data helps us to understand the behavior of the data and allows us to use this linear model to make predictions about the data inside and outside the data range. This is what we refer to in mathematics as a field of modeling. Okay? So, there's all kinds of different modeling. We're just going to particularly work with the linear ones for this section, but there's all kinds. You could do quadratic regression is what it's referred to as. You could do cubics, you could do exponential. There's all kinds of different functions that you can use and model that. So, the table below here has some values, okay? And this is the number of cricket chirps in 15 seconds. And the air temperature that goes along with that. Okay, we're going to plot this data and determine whether the data appears to be linearly related. So, we're going to let this be our x-axis and let this be our y-axis. And notice we have a chart here that doesn't have anything on it. So we have to kind of choose our scaling. I like to always kind of try to do 5s and 10s just because they're nice rounded numbers somewhat. I'm going to try to do 10. So going along the x-axis, these are going to be our chirps. Along the y-axis, these are our temps. And that is in degree Fahrenheit. So if you want to put that on there, I'm going to have to squeeze in my numbers along there. Okay, so I'm going to go along the bottom. And let's see, our lowest is a 18.5. And our highest looks like it's 44. There's quite a few through here. So I might go every other one in 10. Let's say that this is 10, so technically we're going along here on the bottom by 5s, but I'm only marking every 10. So that's kind of a nice spread out version of that. Then on our y-axis, we have a low number of, looks like 52, and the high number of 80.5. So instead of just kind of skipping things here, I'm going to go by 10s and see what that works. 10, 20, 30, 40, 50, 60, and you can just skip every other one. Whoops, 90, 100 if you want, or you can write them off. Okay, now we're set up to plot our points. Now, a lot of these we're just going to have to approximate. So for my first one, 44 chirps on the x, 80.5 on the y. So go 44, which is about there, go up to 80.5, which is about there, and plot a point. Then I'm going to go over to 35, which is right on the line, up to 70.5, which is just right above the line. Then I'm going to go over to 20.4, up to 57, so that's approximately there. 33.66, which I'm going to approximate to be there. 31.68, which would be about there. 35 again, 72 this time, so I'm going to go right above that 70.5. Then we have an 18.5, which would be somewhere around here. 52, which would be maybe about there. And then we have 37, 73.5. We could equate it to about there, possibly. And then 26.53. 26.53, which say is about there. Okay? So the question they ask here, does the data appear to be linear? Now remember, a linear function is a line. So does this data kind of exude a linear or a line pattern? And the answer is, hopefully you can see, that is yes, that does look like a line that I have there. Now, when we talk about a linear regression, or what we refer to as a line of best fit, we can do that by, okay, if I imagine a line going through my data, then I could kind of model that line by writing an equation and then use that to determine different values, to do some projections, and that's the idea of modeling. So I'm going to choose, or actually kind of go through and do a line, and you can eyeball that line so that it goes through like part of the data, where part of it's above, part of it's below, and I'm going to do something like that, okay? So maybe I could have pointed it down a little bit, maybe I didn't, I'm not for sure. That was my eyeball line of best fit, okay? Now notice on this line, there are points. There are points along here, but those points are not data points necessarily. Now this one is, looks like that one is. This is a nice point that kind of crosses the grid pattern at 2560. What we want to do is to see, are there a couple points that I could use to write the equation of the line? Because that's all I need to write the equation of a line. Now, actually, let's see. The trend of our data, let's take care of that first. It says, as the number of chirps does what? Well, let's talk about, as the number of chirps increase, is what I'm going to put there. Let's see what happens on the temperature. So as the number of chirps go up, what happens to my temperature? My temperature also goes up, or it increases as well. A lot of times if we have these kind of questions, you're looking at kind of the behavior of the data. Does it go up? Does it go down? As one goes up, does the other go up? Or does it go down? So those are the types of questions that you want to kind of ask. So now that I have this line of best fit, now again, you can choose any of the points on that line. I could choose this point that isn't even part of my data, but I could also kind of see these 2 points here that are part of my data that I could also choose. So it doesn't have to be. I'm going to put an X on both of those because those are the points that I'm going to choose to help us out, okay, to write the equation of the line. So this is the one that's right after 20 up to about 50 something. So that is this point, 20.4 and 57. So with 20.4 chirps in 15 seconds, it's 57 degrees Fahrenheit. And then the other point that I have here is the 37 one and 73 and a half. So I'm going to choose 37 and 73 and a half. So again, those points could be data points. I could have chosen this 2560 also as a point on my line. Doesn't have to be points on or in the data, okay? So now let's write the equation. So in order to do that, we have to have 2 points. Just like what we've learned in chapter 2, from 2 points, I can find a slope between those 2 points. And I'm going to do y minus the y. So 73.5 minus 57 all over the x minus the x. So the 37 minus 20.4. And I can get the not so nice numbers as 16.5 all over 16.6. Now, you can do an approximation as a decimal, but it's going to be a really nasty decimal, okay? I'm looking at these numbers and noticing that there's one decimal place in each. So if I want to get a reduced fraction here, I'm going to multiply this by 10, which moves the decimal to the right. Multiply that by 10, which moves the decimal to the right one spot. And I end up with a fraction that is fully reduced, okay? Now, it's very, very, very close to 1. If I would have had that 166 over 166, then that would mean that I have, for every 1 chirp, or excuse me, for every 1 degree Fahrenheit that I have going up, that means I increase by 1 chirp as well, okay? So making meaning to that. But we're not kind of focusing too much up on that. What we really want to focus on is getting that equation. So we have to write that equation. Now, as you recall, there's something called point slope form that we like to start with and then get our equation down into y equals mx plus b. So I know what the slope is, so I'm going to need that, and I need a point. Doesn't matter which point that I choose. I'm going to choose, say, this point to be my x1, y1. And once we identify those 2 things, I'm going to plug it in right here. So let's go y minus the y value of my point, which is 73.5, equals the slope, which was 165 over 166. Make sure you reduce that fraction as far as you can, times x minus the x value of my point, which in this case is 37. Now, that's the point slope form, but let's go ahead and get that into y equals mx plus b form. So in order to do that, we've practiced this before, I need to distribute. And when I distribute that fraction times x, that's just 165 over 166x, minus, when I multiply this times that, you can go straight across. You can use your calculator if you want, but you should get 6105 all over 166. Okay? And to finish it off, I need to move this 73.5 over here. So I'm adding 73.5, adding 73.5, which is a fraction plus a decimal. That's perfectly okay. Don't panic. So I get y equals 165 over 166x. I'm just going to rewrite that first term. And when I combine these and get an improper fraction, again, if you're not used to doing that by hand, make sure you know how to do it on your scientific calculator. If we need to kind of work together in order to figure that out and get you solidified, then we need to do so. So it's kind of a not so pretty fraction there as well. 3048 over 83 is our reduced fraction. Okay, so now that we have an equation that's modeling our data that we have, so that's the equation of this line, we can now start asking different questions about that data. To be able to project temperatures, we can project the number of chirps depending on a temperature. So this next question says, now that we have our equation, what would be a guess of the temperature, which is the y values, outside when there were 25 chirps? Remember, those were my x values that I had out of the table. So using this equation, given x equals 25, can we find the y value? And the answer is absolutely. I'm going to plug that x value of 25 right into that equation, and I'm going to multiply 165 over 166 times that 25, and then add on to that 3048 over 83. Now again, that's just a calculator thing for you. Multiply and then add. I will tell you as the decimal, we get 61.57 degrees Fahrenheit. So that would be the projected temperature from our line of best fit. Just from our eyeball line. Now at 25, am I approximately at 62? 25, we're at approximately 62. Now this is freehand, so that's why it doesn't look exactly like around 62, but we are close. So when we do something within our data range, 25 was within our data range. We had values that were to the left of 25 up here. We had values to the right of 25. That is what we call interpolation. Okay, this is referred to as interpolation, because you are making a prediction within the data values that you have. Now, if I were to say, okay, I have 56 chirps that I want to know what the temperature is for that, then that's outside of our data values, and that's what we refer to as extrapolation. Extrapolation. So we had extra values beyond what we are given. Okay? All right, so that's doing it by freehand. That's by being able to do a line of best fit. But while eyeballing a line works reasonably well, there are statistical techniques that we can use to fit a line to some data that minimizes the differences between the line and the data values. This technique is called least squares regression, or most widely probably known as linear regression. Least squares regression, or a lot of people refer to that as linear regression. Now, this is a very involved formula that I'm not going to go into, but it can be computed by many graphing calculators, spreadsheets, statistical software, and many web-based calculators. So we will be using a web-based calculator for this, unless you want to just use your calculator. If you have a graphing calculator, it's very easily figured out how to use. I'm sure you Google it on the type of calculator, or do a YouTube video on the type of calculator you have on how to do a linear regression, and something will come up. But this also right here, I did a URL shortener, but brings up a calculator. Let me get to it real quick here. Right here, that is called Math Portal. So it's kind of cut off just a little bit from the view that you're seeing. But it's asking us for correlation and a regression calculator, okay? So we can, from this little calculator, scroll down, and here's kind of where we do some input values, okay? We're going to input our x values, input our y values for this situation with the chirping. So I'm going to pause the video now on my own, and then I'll come back on. I'm going to enter those numbers in at the computer. That way you don't have to wait. So hang on. Okay, so now I'm back. Notice that when I entered in the values, you can either separate with a comma or do a blank space. So I just went ahead and put the blank space. So that's exactly the values that we had in our table for our x's, for the chirps, and this is the values for our y's for the degrees that we were looking at. So I scroll down and I have two options. It says find the equation of a regression line, or this one's to come. We'll come back to that. So I'm going to, at this point, find the equation of the regression, and I'm going to keep scrolling down, and I want to say compute. So it's working, and it comes back. Let's scroll down, and now it has all this data, and it actually did a nice graph for us, and it gave us kind of a more specific line with the regression. And notice right here, this is the line that we're looking at. So y equals, now they kind of flip the x and the y, but that 1.143 was like our 165 over 166. So notice ours was a little bit off because ours was less than 1. This one is just slightly bigger than 1. But this is what the computer or statistics shows that it is the line of best fit. So when we go back to our notes, the linear regression line that we were given, I'm going to do it in the y equals mx plus b form, okay, is y equals, it was 1.143x plus 30.28. And that is saying that's the ideal line for the data that was entered. Now, we could use that line again. Can we now use this equation, which is different from the one we found, to project the temperature with 25 chirps, which is what we did with our eyeball line, or our line of best fit. Let's see how close we are. If I have 1.143, multiply that by 25. Obviously, these are rounded numbers, so we're going to have a small adjustment just because they are rounded numbers already. 30.28 is what I would add at the end when I multiply and add. This will be 58.855 degrees. Okay, so we had 61.57, so we're close. We're relatively close. We're not exact, but you'll never get exact when you're dealing with a line of best fit that you just eyeball and put on paper. Okay, so be able to know how to kind of do a line of best fit on your own. Also be able to work that website to find a linear regression for a situation. So most calculators and computer software will also provide a correlation coefficient. Now, a correlation coefficient basically is a measure of how close we are to, or how close the line fits the data. So ours would be off way more than what the computer says because the computer's using that specific formula to help us out. So we can also do that with that software, but let's first define that correlation coefficient. The correlation coefficient is a value R, usually represented by an R, between -1 and +1. If that R is greater than 0, it's positive, okay? This suggests a positive relationship with our data. So it means that our line is doing something like that, or our data is kind of in that form. If R is less than 0, then it suggests a negative relationship with our data. So I would have a trend that looks something like that. Now, the closer that our value is, if I can get that off, Okay, there we go. Sorry. The closer that our value is to 0, the more scattered our data is. And we'll see some of that in just a minute. The closer our value is to -1 and +1, maybe I should say -1 or +1, then the less scattered that our data is. It's a little bit more tight. It actually looks like a line if we are closer to -1 or +1. The only difference here is if it's -1, it has a downward trend. +1 would have an upward trend. So here are some examples of some correlation coefficients so that you could kind of see. Notice these zeros that are down here. This is data that's just scattered all over the place, and this is simulating lots of data here that we have within this. Notice that the ones are very close here with 1 and -1. Notice they are nice line figures. But if you look at these that are kind of trending, notice here this is a tighter fit of data in a negative fashion. This kind of has that, but it's not as tight as this. This is all over the place. Therefore, our correlation coefficient is 0. So the closer you get to 0, the more scattered that it gets. The closer you get to -1, the more tighter it is in line. Likewise, when you have a positive, this is closer to 0 than 1, therefore it's not as tight. We're getting tighter here with 0.8 and with a 1. So what is our correlation coefficient for our cricket example above? That means we got to go back to our calculator, okay? So on this website, if you just scroll down after all that, now notice here, woo, there's that formula I was talking about. I would much rather just do that by a calculator than by hand, okay? And I like numbers, but that's a lot. Now, keep scrolling down after you found that linear regression. Notice the website keeps your data in place, gives you the opportunity then to go and find that correlation coefficient if you so choose to. And I'm going to hit compute, and we're going to scroll down, and voila, there it is. Our correlation coefficient for the regression line that statistics says is the best line is 0.90 or 9509. So, So R here is equal to 0.9509. Now, what does that mean? Is that close to 1? Is that close to 0? Well, if I were you, I'd say that R is very close to 1. Okay, now, if it is close to 1, what do we know? It's close to 1, so that means that we have a strong relationship here that is linear. So we have a strong linear relationship. Basically, it's forming a nice strong line there. Okay. Now, we also have to kind of assess the sign of that R value. So if we end up having that R value to be positive or negative, that's what we have to kind of look at. And in this case, that R value is positive. Therefore, we end up having a positive relationship. Now, didn't that work? Doesn't that mean if I look at my scatter plot, which is what we also call just a graph of points, if we go back to the first page, notice that we did have that positive increasing pattern with our line. Therefore, that R value should be positive. It should be greater than 0, which it is. Okay, so it would be a strong linear relationship, and we also have a positive relationship where it is going upward. So that's what we're doing basically in section 2.4, making sure that we can do a line of best fit, making sure we understand that idea, and then we'll use that website in order to compute some of those regression lines in the y equals mx plus b form, and also compute some R values here so that we can determine how strong that pattern is and what kind of relationship that I have. So practice some of those, and we'll get into some absolute values to end chapter 2, and then we'll be able to do our assessment over that chapter. So until next time.